A voltage divider circuit looks like this. So I have some input voltage, which I'm going to call V in, and I connect it across a network of two resistors which are connected in series. So I might call this one R1 and I might call this one R2. And then I define an output voltage across one of these resistors. So for example, I might choose R2, and then I will define V out to be a voltage measured across that resistor. So once I've defined this circuit and set up this circuit, I now have a thing called a voltage divider. And the way that a voltage divider works is that my output voltage V out is given by this equation. So I have V in multiplied by the resistance across which my output is defined, in this case it's R2, divided by the total resistance, that's R1 plus R2. And so this is useful because what I have here is a linear relationship between input and output voltage, and I use this to scale down a voltage by a fixed ratio or a fixed amount. Basically, this is a linear relationship from input to output. Linear relationship between V in and V out, controlled by the resistors that are used. So if you had a signal that goes from 0 to 10 volts and you'd like to scale it so it instead goes from 0 to 5, a voltage divider circuit is what you would use to achieve that task. So another way that I can write this, which you might find useful as far as trying to memorize this pattern, goes like this. So if I have my input voltage and the two resistors that make up my voltage divider circuit, and I define my output voltage to be here, then I can call this one R out, which is the resistor across the output. Then I have this equation that voltage at the output is voltage at the input multiplied by resistance of the output divided by the total resistance of the voltage divider network. And so this is a useful way to express it because I could also have defined my voltage divider circuit like this. I could also have said I've got V in and I've got two resistors, but instead of using the bottom resistor, I use the top resistor. This is also completely fine. Still a voltage divider. There's an output voltage. Let's call this one R out for the resistance of the output, or the resistance across which the output is defined. And this one is nice because I can use the same equation. So it's V in multiplied by R out, the resistance across which the output is defined, divided by R total. R total here is the sum of these resistors. Let's just remind ourselves where R total is the sum of both resistors, because they're connected in series, so we just add them up to get the equivalent total resistance. So that's kind of one way that you might prefer to express this for your own memory of how this actually works. So again, this is a really common pattern in circuit design, and so you need to be able to recognize this, and you should be able to just write down, just straight from your memory, write down what the equation will be for the output. If you can't write this down from memory, then you can solve for it using Kirchhoff's voltage law. There's a proof in the textbook that shows how this works, but it's a common enough pattern that you should actually just know it and recognize this, how this works. Now, there's one kind of practical concern that is important for you to recognize, and that is the impact of the circuit that we actually connect to the output voltage. So we would call that the impact of the load. So in circuit terminology, the load is whatever we connect to the output of this current stage. So if I'm designing this front end stage of my circuit, which produces an output voltage, the thing that I connect to that output voltage is the load for this part of my circuit. So the impact of the load. So let's draw a typical situation, and then we'll have a look at what that means. So let's set up my voltage divider, resistor 1, resistor 2, connected in series, and I'll define my output voltage like this. So I'll say R out, let's call this one R1. My output voltage is here, so that's V out. And I say, well, okay, that's good, but now I'm going to connect that to something. And let's suppose that the thing that I connect it to, I have simplified its circuit. I have simplified its circuit into a single resistor. So it was a big network of things, right? Series, parallel, whatever. I've combined them into an equivalent resistance R load. So this is what a voltage divider circuit might look like when I'm actually using it. Now, what's the implication of this? Well, what it means is this output voltage, I should draw that back on. Output voltage is here, V out, being the voltage here, voltage across this combination of R out and R load. So that's my output voltage. Now, what I have here is a combination of two resistors in parallel. So you should be able to recognize that. You should see that these are two resistors in parallel. Two resistors in parallel. Which means that I can combine these together. So I can combine this into an R equivalent. And the R equivalent for this, because there's two of them, I can use that special case, which is the product divided by the sum. So that's R out, R load, the product divided by the sum, R out plus R load. And so now the expression for my voltage divider is going to look like this. So V out is Vn multiplied by, in this case, the resistance across the output is this R equivalent, right, that I just calculated from here. So this R equivalent divided by the total, which is going to be R1 plus R equivalent. So you see, if there is a load, then the output voltage will change. So that's kind of a weakness of this design. If there is a load resistance, then the output voltage will change. Now, what you might think about is, well, how much actually can this change? It will depend upon the value of the load resistance. In general, the larger the load resistance, the less impact we will see. So large load implies small change in V out. And you can kind of analyze these equations and put some numbers in, and you can see that for yourself. And there's a tutorial problem this week where you're going to look at the example where you have some load resistance attached to a voltage divider circuit. But in general, when we're kind of measuring the voltage of something, we would like the equivalent resistance of that measurement circuit. So we would like R load. We would like for that to be large. A large value of R load means that we will not really perturb the voltage divider circuit very much. And of course, when I say large here, of course, this is a little bit vague, right? What do I mean by large? What I mean by large is in comparison with R out. So that in that network of parallel resistors, if R load is much, much, much bigger than R out, well then R load doesn't impact very much on that equivalence. And you can see that by looking at the structure of these equations. So the definition here of R equivalent, you can experiment with putting different numbers in and you can see the impact that you will have. But yeah, basically a larger value of load resistance means a smaller change in the output voltage. So that's a useful thing to keep in mind.